Okay, everyone, Wednesday, kind of your last lecture. Friday's a review session, right? I'm going to do something a little different. What I'm going to do is, notice I've written summary. What I'm going to do is I'm going to try to not only summarize this class, but PChem 1, PChem in general as well. So I'm going to talk a little bit about PChem 1 and PChem 2 simultaneously, and we're going to talk about where some of your equations from PChem 1, some of your thermochemistry equations came from via PChem 2, this class. Now, I'd hope that the reason is to provide a summary for PChem in general, which I hope you'd appreciate. But really what I'm doing is, I wasn't going to do a last lecture. I think I even mentioned that. I was just going to post the review session early, and I'm still going to try to do that, but to be blunt, I've been overwhelmed. It's bad. we're barely going to do this on time, but we will do it. We are going to get this done. And that means I'm still writing the final exam. I'm mostly done, so I'm going to go ahead and film the review session tomorrow, and I will put today is Wednesday, right? I will post the final review session by the end of the day today. So you are kind of getting it early. And remember, the final's on Wednesday, 1 to 3. Now, when I say that the summary is actually a review, I'm going to be reviewing some Boltzmann equation stuff. So more towards the first of the semester, which is good because that's probably the stuff you forgot. Let me also state that if you're not studying for the final, you've dropped a letter grade by now. There's no fixing that. And remember my analogy of if you are studying for finals during finals week, you're trying to put too much through a door at once, and all of it gets stuck, right? It's like the Simpsons analogy. So to whatever degree you can minimize that whenever you're watching this, start studying now, and remember, never forget this one. If you're going to spend 5 hours for every class, what does it matter when you do it? You're going to spend the same amount of time. If you pace yourself, you'll win. If you try to do it all at once, you'll lose. Either route takes us 5 classes, 5 hours, 25 hours. Either course costs 25 hours, but the route changes the result. So, but anyway, I've said that a zillion times, so I'll stop talking about that. Okay. Now, what am I talking about in terms of the summary? What I mean is, let's think about PChem 1, and I'm going to do O2. What is the internal energy, right? So, at least when you didn't have PChem 1 with me. When I teach PChem 1, typically the first and second part, the first third, second third of the class is all delta U, delta H, delta G, on and on and on. And so of course we start with internal energy. And internal energy, I've brought this up a couple of times via the equal partition theorem. It's 1/2 RT or kBT, and I like kB in this class, right? The gas constant divided by Avogadro's number. I like that in this class. So I'm talking about a single molecule, 1/2 kBT times degrees of freedom, right? The degree of freedom is 3 translations. For everything. Everything can translate in 3, X, Y, Z, because, 3D universe. Okay, then you add rotations. Now, for oxygen, there's only 2, right? There's this rotation, so I'm holding on to the oxygens. There's this, then there's this, but there is no toral, right? There's this. That is not real. That's not real. You can't bowl an atom, right? That doesn't. An atom's surface is made of the electron, and you can't roll that. That doesn't even make sense. If you were to try to roll it, the electron whizzes around on its own a billion times before you would perceive it rolling even once. So oxygen, linear molecules have 2 rotations. Nonlinear have 3, and then you have vibrations. And of course you have 3n minus 5 for linear, 3n minus 6 for nonlinear. So that would be 6 minus 5 is 1. There's 1 vibration. Of course, O2 can only vibrate this way. Of course, right? But recall that you don't count that. That doesn't count because what happens is a vibration takes so much energy that at room temperature, you can't input or take out energy. And so thermochemically, it doesn't participate in anything. So, and again, I don't know how that was taught, but that's my explanation. Okay, so this ends up being 5. 1, 2, 3, 4, 5. 5. So oxygen's U is, of course, then 5 halves, kVt or RT. And the heat capacity at constant volume is the change in U with respect to T at constant V. And so that'd be 5 halves kVt or 5 halves RT per mole. And sure enough, if you look it up, just Google it, and type 5 halves, use RT, right? 5 halves, 8.314 times, oh, sorry, there's no T, right? No T. The derivative with respect to T makes it go away. Ugh, I should refilm that. Anyway, so 5 halves, and then it's usually done in joules per mole, so you use, so 5 halves are 8.314. You can type that into Google, it'll give you an answer, and then you could also look up the heat capacity at constant volume of oxygen, and you would see pretty much identically the same number. Okay, so again, trip down memory lane. This is not on your test, and why am I talking about it? Because quantum mechanics will prove this. So, you know, if you have U in heat capacity, then you have all the thermochemical stuff, right? Enthalpy is U plus nRT. So now you've got H. Then to do temperature changes, you use heat capacity. Heat capacity at constant pressure is equal to heat capacity at constant volume plus RT. So, you know, when you have when you have internal energy and heat capacity, you actually have just about everything. Now, here's my point. I'm going to show you how you learn to actually calculate this. Right? Remember, this is macroscopic, and what we did was microscopic. We talked about oxygen atoms. We talked about quantum mechanics and Boltzmann's equation. Those combine, and we're going to get this. So notice that, again, I'm summarizing, but I'm really reviewing. I'm reviewing for your test, because I told you I was going to do that. Okay, now, the question is, how do I do that? Okay, so we're going to do translations, rotations, and vibrations. We're going to figure out our quantum Boltzmann equation, and then we're going to get to that. Okay, now what's the quantum for translation? So what, you know, I don't recall us ever discussing the quantum mechanics of translation, right? We didn't. That is actually a subject, but you know what I can do is I can just say that an O2 molecule is a particle in a box. Three-dimensional box. You know, that we've covered. Okay, now I'm going to do just, let's just start with one dimension. And we'll solve everything, and then I'll show you how you do the 3 dimensions. And what we're going to do is calculate the average energy, which would be internal energy in the language of PChem 1. Okay, so particle in a box, and let's make the box infinite. Let's make it as easy as possible. 0 to L, there are wave functions, there's the ground state, there's the first excited state, there's an infinite number of them, yada, yada, yada. And you may recall that the energy from boundary conditions was n squared h squared over 8 L squared. Okay, now, hopefully you remember some things about the particle in a box. The boundary conditions did take the wave functions. Once we have the wave functions, and what is that? That's sine. There's a normalization, sine n x over L, n pi x over L. Yeah, square root of 2 over L. I'm doing that from memory, so hopefully that's right. That's the normalization constant. So we had boundary conditions, we got the wave functions, those are the solutions, and with the solutions, we can then figure out things like energy, and then you even did things like spectroscopy with it, right? So remember I was telling you that, you know, you set up the problem, which gets you the Hamiltonian, the solution are the wave functions, and then the wave functions you do, you know, really a lot of things. Now, at the beginning of class, we just would write down the energy, but later we could do things like spectroscopy, transition moments for particle in a box, and there's really a whole bunch of other things if we had time to do them. Well, like here's one of them, right? So what else can I do with this? All right, so what I want to do is now calculate the average energy. And this is one dimension, so what we're going to do is we're going to find, let me go ahead and give it to you. It's going to be 1/2 kBt, right? So this is one dimension, it's x, and we're going to find energy, which unfortunately is the same thing as U. So we have two letters for the same thing. Sorry, you know that happens a zillion times. We're going to find it's 1/2 kBt. And then there would be another one for Y and another one for Z. And there we go. We get our three translations, and that's going to contribute 3/2 kBt. And then we'll do vibrations and on and on and on. Okay, so I've already given you the answer, but now we do have to do it, right? Okay, now how would I do this? Well, for one, I know that H, 8, and M, L, all those look like constants. So what I'm thinking is I'm going to want to calculate the average n squared. But before I do that, let me write the probability distribution. So the goal is the average energy. Now, what do we want to do? What I really want to do to get the average energy is I need the probability distribution. So here's some quantum, but now I'm kind of going backward to the very beginning of class when I talked about Boltzmann, so I'm not quite doing this in order of the class. Sorry about that, but whatever. Hopefully, you know what this is, right? That shouldn't matter. Okay, probability, the Boltzmann distribution is E to the minus energy over KT. So E to the minus energy in H squared over 8 mass L squared kBt. Okay, so that's a probability distribution of having some particular energy over the sum of all possible energies. You just write the same thing again. You ever notice that? You just write the same thing again. You just have a sum. And often that sum will turn into an integral if the thing is continuous, like for velocity. When it was like photons, you had to have an identity with a sum because you only have 0, 1, 2, 3 photons. You don't have fractions of photons. So anyway, we talked about that to death. Okay, so this is the Boltzmann distribution. Now we did want to worry about how does this part go, and I want to remind you that the particle in the box, the lowest that n can be, the quantum number, n sub x, n, whatever, it has to be 1, right? There's no 0. The harmonic oscillator has a quantum number ground state of 0, 0, 1, 2, 3, on and on and on. Now, remember that one was weird. Mostly quantum numbers tend to start at the number 1. Every problem is different. But so anyway, so the normalizer starts with n equals 1. Of course, particle in the box, there's an infinite number of excited states. So that's how I set up this thing. Okay, now here's where, again, we really need to do some reviewing. Whenever you have one of these Maxwell-Boltzmann or Boltzmann type questions, what's the average velocity, what's the average number of fish in a barrel, the first thing is to do the normalizer, right? Because this is not helpful as it is. It needs to be a bunch of constants. Constants are easy, right? I can just type them into Google and it says, the result is 1.5 to the 9 joules, or this is just a bunch of letters, right? So that's not very helpful. Okay, so what do? Okay, now in this case, I had to spend a couple of hours, to be blunt, on Google figuring out how to do this. I tried to find a summation identity because, n is going like 0, 1, 2, 3, and they don't exist. So in other words, this is undefined. So I thought, there's no way to do this. I thought that was weird because I'm pretty sure there is, right? In fact, I already told you there was an answer. Okay, now it turns out that what you do is there's an approximation to do this. And we're going to do an approximation of turning it into an integral. You've done that a zillion times. This one's a little bit weirder than others because it's kind of hard to justify turning it into an integral. But here's how you do it. You're going to turn this into an integral. So this top part is still the same. You're going to turn this into an integral. Lower limit of 1, upper limit of infinity. and e to the minus nh squared. All this stuff again. Sorry, I'm writing that really small. I hope you don't have too hard a time seeing it. And of course, we're summing over n, so we're integrating over n. Okay, the way that this is justified for the normalizer is if L gets very big. So if L gets very big, you notice how you have n over L squared? So you can kind of think of that as like going together. If L gets very big, then this summation and this integral end up getting closer and closer together. So now I remember I said that there's no solution to this summation. What I mean is that there's no equation. So what I did was I can sum this on a computer. And the thing is that it's just going to come out to some number. And again, that number is not equal to some closed form. It's not equal to like, h bar over 5 or anything like that. When you sum this, it depends on what numbers you plug in for mass and length and all that. Okay, now so understanding that, when I plug in a bigger and bigger L, like, several nanometers and whatnot or bigger, and then I evaluate this integral, then they end up becoming closer and closer together until they're like the same to like 10 significant figures if L gets very big. Okay, then the next thing is this lower limit of 1, make it 0, for the same reason. What happens is as L gets bigger and bigger, the lower limit of 1 or 0, it changes it to like the 10th decimal place. Who cares? When things aren't changing to like 3 decimal places, then we really don't care anymore. Okay, so again, Boltzmann equation, we have to solve the normalizer. This one's kind of weird. There's no equation for this, but unless L gets very big, in which case we can approximate it as an integral. And of course, guess what? Now we need to find an identity. So we look at the cheat sheet, and you find this in the cheat sheet. It's one of our standard ones. You probably can look it up online. Well, of course you can look it up online. You can look it up. You can actually just type this into our little math equation websites, which I like so much. And so there's that. Okay, so then what's this whole thing equal to? E to the minus. I didn't give myself much room, did I? Okay, so there's that on top. Equal signs there. Okay, now what's on bottom? All right. Okay, so I'm going to have a square root of, so a big square root, and I'm going to have something on top and bottom. You see, I didn't give myself enough room, did I? Okay, pi on top. So hold on, 8 ml squared kbt pi over 4 h squared, and okay, so 8 over 4 is 2. There we go. And let me check if that's right. Yeah, that's right. And okay, so there you go. And now let me, one of the things that I notice you folks get confused is once you solve the normalizer, remember it's in the denominator. So when you write that out nicely, you would flip it over. So I'm flipping it over, right? And I'm going to write 2 pi m because it looks a little bit better. Okay, there we go. And then we still have e to the minus all this stuff, 8ml squared of kbt. Okay, and I'll just keep working down. Okay, so big picture, probability distribution, some way of solving the normalizer. Again, I'd explain why you have to solve the normalizer. This one's kind of interesting because I told you that you have to have L get very big, but really what you're doing is you're bridging like from quantum to classical. You're getting more classical behavior, which is, when Isaac Newton's in the driver's seat when force is mass times acceleration. None of that applies to quantum mechanics. You have a completely different set of equations for even motion when you do quantum mechanics. But what happens is there has to be some way that quantum mechanical things behave like, cars and people, classically. There has to be some crossover behavior. And you're actually observing that here. When I make this summation into that integral, because L is big, that's when you're going from quantum to classical. So I thought that was kind of neat. But of course, really, it's just a way to solve the equation. All right, now that I've got the expression for the probability distribution, meaning again, I solved the normalizer, now I want the average energy. Okay, now here's another trick, and I tried to get you to do this a couple of times. I'm going to write the energy down again. I keep forgetting, oh, you know what I've done? I keep forgetting n squared. Sorry about that. It doesn't matter actually at this point. So sorry about that. Sorry about to mess up your notes, but you know why I noticed it? Because it only matters now. Now that we're going to calculate average energy. Remember, the reason that this isn't h bar is that when we solved this, the solution had h bar, but we factored out the 2 pi because it made the answer a little bit nicer looking when we did that. Okay, so anyway, I'm actually just writing down the energy of a particle in a box, which I wrote up there. And why am I doing that? Now again, you've actually had several questions like this, and it kind of, I think over half of you got this, but it would have been better if all of you got this. Okay, so when you have an equation like this, and now what I'm trying to do is calculate the average energy, and these aren't necessarily going to be the same thing. What you want to recognize here is that the only thing to be averaged on this side would be n squared. And the reason is that h is a constant, 8 is an 8, mass, we're going to assume it's constant, and L is also constant. So what else could you take the average of? So that means that what you're really after is n squared. Now, the reason that's important is that's what we're going to use our Boltzmann distribution. So we're looking for just n squared. And these things haven't gone away, right? It's just that they're not really important. Okay, now what does that mean? Okay, so now to get the average of n squared, what we're going to do is we're going to take the integral over all limits of the probability distribution, which is a function of n, and we're going to ask for the average n squared. And that means that you take the thing you want the average of, which is n squared, and you multiply it by the normalized probability distribution, which has a bunch of constants, which, even a well-trained dog could deal with these constants because they're just constants. So all of this can go on the outside of the integral, and you don't have to let it blow your head off when you're trying to solve it. By solve it means you're just looking for the right identity. Anyway, so, okay, n squared, the thing we want the average of, the normalized probability distribution, and so now I can't screw up that that's n squared, and I'm just writing this n squared, h squared, 8ml squared, for the zillionth time. Okay, so now I've got the average n squared once I do this. And what do? I look at an identity. And what's the identity? Let's see, I'm almost painting myself in a corner again. 0, again, from a previous homework or online or from the website. So when I write those identities on your homeworks or exam cheat sheets, either I cut and paste them from a previous exam, or where did I get those? I got them from those websites, the Wolfram websites. It's actually faster to just type it in and hit go than to actually try to look them up on Wikipedia or something. Okay, so what is this? What is this? This is, kind of complicated. Square root of pi for a to the 3 halves. Okay. All right, but notice that we're done. Right? These constants come out. N is integrated away. Remember, n squared is x squared. Square root of pi, 4, and a to the 3 halves. You have to recognize that a is h bar squared, 8ml squared kBt. That's all you have to recognize. Okay, so let's put all this together. Give myself a little bit more room. Constants come out. Should have, again, I really messed up. I need to give myself more room here for everything. That doesn't look good. There we go. Okay, the constants come out of the integral. Then what have we got? We've got square root of pi. We got 4 on the bottom. Okay, now let's see. A is, okay, this gets confusing, right? Because you've got A on the bottom and A is a fraction. I hate it when you run into that. You know, the denominator is a fraction. What do you do? Okay. Well, what's on top of A is on bottom of the answer. So that means that I've got h bar squared to the 3/2, which is, sorry, not h bar, h squared to the 3/2 is h cubed. Okay, so not too bad. Okay, then I've got L squared on top to the 3/2, which is L cubed. And then the rest of the stuff I can't do too much with. So I've got 8m kBT to the 3/2, and that doesn't, you know, it's not easy. So what you do now is you start going through this, and I can already see, I'm not going to go through all the algebra, to be blunt. I wanted to end a little early today. Let's see, so I'm going to have, is this right? I'm just going to check one or two of them. I got L cubed over square root of L squared. So yeah, that's right. So anyway, it all makes sense. Okay, so that's the average n squared, and therefore the average energy, which is average n squared, I've already written it, h squared over 8mL squared is 4 over h squared. I'm writing this all over again. I don't know why, it's kind of stupid. Okay, so there's n squared, and I've got h squared on top over 8mL squared. L squareds cancel. 4 over 8 is 1/2. M's cancel. 1/2 kBT. Okay, so there you go. All right, now big picture. Now again, I've already mentioned that unfortunately, when I say energy in quantum, I've actually been talking about internal energy U. Sorry, it's a screw up. Quantum got, you know, like all the examples use E, and when you do thermo, it's always U, and no one thought to make sure that those were the same, and now we're like stuck with it, so sorry. So this is the average internal energy, and it's, and notice that it's the same as the translational degree of freedom for something in one dimension. And why wouldn't it be? What can a particle in a box do? It can just translate. That's all it can do. It only has kinetic energy. So, oddly enough, if the box gets big enough, it's the same thing as the equipartition theorem. 1/2 kBT for a degree of freedom. Now, motion in a single dimension, which is what we solved, is 1 degree of freedom, therefore has 1/2 kBT of energy, 1/2 kBT of energy. So notice how we've bridged your thermo from last semester. We did some quantum mechanics, which was really one of our easier ones, right? Boltzmann equation, which I know that there's a hideous mess of letters, but really, come on, it was just a bunch of identities, right? And a whole soup of constants. Yeah, now it's a little sucky, but you know, algebra is a middle school skill, right? So there you go. Now, of course, if you include the other degrees of freedom, then you have your 3/2 kBT. Okay, halfway there. Now we have to do the rotation and vibration. There's a little bit of a trick there. Let me get a new pen and take a small break, wipe out the board. We're going to do those. We're almost done, actually. The next ones are actually kind of easy. Okay, now the rotation part. So we're going to do this the same way. Define the energy, do the Boltzmann equation, then do the normalizer, solve the average energy, And what are we going to get? Well, we're going to get, let's see, we should get 1/2 kBt for every rotational degree of freedom, and O2 has 2 rotational degrees of freedom. So we should get kBt at the end. That's going to be the average energy. So we'll have 3/2 kBt from the translations, plus 1 more kBt from the rotations, and notice that then we've got the internal energy of O2, and we will do a little bit about the vibrations as well. Okay, what is the energy of rotation? Now I want to point out that in our discussion of rotation, a rigid rotor, 3D rigid rotor, I was focused on an electron moving around a nucleus, and there can be differences when we're talking about molecules, especially if they're 3D like methane or proteins, right? It turns out that I'm kind of lucky in that a lot of the equations for diatomics, you have to be a diatomic to rotate, right? Remember that trick question on exam 3? How does argon rotate? How does the argon atom rotate? It doesn't. It's just an atom. Okay, so when it comes to diatomics, it turns out that all the stuff we learned for the hydrogen atom, for it rotating, the electron, is the same. If we did something like methane, then we'd have different equations. And I didn't cover that because, to be blunt, it bores me to death. Number 2, a lot of molecular rotation, quantum mechanics of molecular rotation, you did that in Pekin Lab. So that's one reason I backed off on that. Now, regardless, again, I'm lucky that the quantum mechanics of diatomic rotation is pretty much the same as what we covered, which was mostly just worrying about that electron on hydrogen, right? Because after we did the 3D rigid rotor, we went straight to the hydrogen atom, if you recall that. All right. So what's the energy? Again, it is the same equation, h bar squared L times L plus 1, which is our quantum. So notice I'm doing the quantum mechanics over 2I. I is the moment of inertia. Mass times the bond length squared. Okay, so therefore, the Boltzmann equation, so I have to define the Boltzmann equation, the probability that we have a certain energy, which is dictated by L. And I have to give myself some room here because one reason I'm covering this, I've already given the answer, so why am I even talking about this? It's because there's a little bit of a twist here. You haven't seen this yet, and don't worry, it's not on the test. But when we do Boltzmann things, we have to keep into account degeneracies. You didn't have this when we did Maxwell-Boltzmann or any of the other stuff that we talked about, like Maxwell-Boltzmann or cats in a house or COVID patients. Degeneracies never came up, and to be blunt, I made sure of that. That was like something I engineered to make sure it didn't happen because it complicates things. How does it complicate things? All right, for one, where's the degeneracy? Well, one S, there's only one S. 2, right? You got a 2S, then you got 2P. How many 2Ps? You got 3 2Ps. We get N equals 3. You got 3 D states. How many D states? 5. So you got to take that into account. L of 0, there's no degeneracy. You have one state. L of 1 is a P state, so there's 3. L of 2, which is a D state, there's 5. So now you may recall, I actually did talk about this. The degeneracy is 2L plus 1. So what happens is that 2L plus 1, that degeneracy, ends up appearing in the Boltzmann equation. So here is our e to the minus energy that you hopefully are kind of sick of this. I hope that you're sick of it because energy over kBt. Right. Hopefully you're sick of that, but there's this extra bit, this 2L plus 1. Now again, I just want to point out, it's there just because of the degeneracy, and the way to interpret it is, things want to be in the ground state, but due to thermal energy, they use that thermal energy to be in excited states. It will fundamentally change things if there's more excited states, right? If something wants to go from 1s to 2p, it is different if there's 3 2p states, which there are, versus just one 2p state, which is not true. it's going to find its way easier. I think that, doesn't that make sense? If there's more, you know, if we're talking about thermal energy driving something from 1s to a 2p state, it's like easier for that to happen if there's more 2p states. And there are. There's 3 of them, px, py, and pz. But there's only one 1s state, right? 2l plus 1. Okay, now on the bottom, same thing happens. 2l plus 1. Now again, everything, you know, when you do the normalizer, you just rewrite everything except that you have a sum, and maybe that sum turns into an integral. And now we also have to know what the limits are. And here we're it's a little bit easier because L of 0 is the correct lower limit S state, right? Is the lowest. Okay, so now what? Okay, it turns out that now we've got to solve this thing. And as before, it can be turned into an integral. And actually, you know, the reason is that it's very similar to velocity, to Maxwell-Boltzmann. Remember that for Maxwell-Boltzmann, we just basically immediately turned the sum into a sum for velocity x times velocity y, velocity z. We just turned those sums to integrals. And the justification was that velocity can take like any, you know, 0, 0.1, 0.2 meters per second, right? It's continuous, it can have any value. You know, rotation is actually very similar. While it is quantized in discrete L's, the energy spacings are really, really fine. It's basically continuous. So, and that's why, and you know how you know that? In PChem lab, that vibrational structure, you have just one vibrational line, but the rotational lines, there was like a zillion of them, right? That's because it's kind of continuous. And that's why we can approximate this as an integral. And so actually, I'll tell you what, now just keep track of what I'm doing. I'm just going to do the normalizer. I don't want to have to write that stuff on top again. Okay, so the normalizer, we're going to turn the sum into an integral, which is really well justified. 2l plus 1 e to the, I'm writing this over again, which sucks, but I should just PowerPoint it, right? And what I did here, I ended up having to use the normal website won't do this. This is a little too complicated. You know how sometimes it hangs up sometimes, especially if you don't type things right, or if you give it too much, it hangs. So what I did was I had to use, you know, I don't know how to do this, okay, by hand. I just have better software that gives it faculty. So, and so what I found was, here, where's my identity? So basically it was like this, integral 0 to infinity of 2x plus 1 e to the minus a x times x plus 1. So that's how I did it, and it is 1 over a. So it's, you know, this actually kind of looks definitely a little bit more complicated. I was really surprised that it came out to be such a simple identity, but you know, whatever. Okay, so what is this? Okay, so this is just two. I have to have my this is too complicated. I'm not going to do this off the top of my head. Just 2i kBt. It's just the inverse of the argument of the exponential over h bar. Well, that's h bar. Do I h bar? Yeah, sorry, I missed the little h bar. Okay, so that's the normalizer. Now, you know, one problem that I had with a lot of you folks, you know, we've done this question many, many times. Some of you sometimes stop here. You just solve the normalizer and you're like, well, that's the answer. No, you may have noticed when you got half credit, we're only half done. Okay, so now what? So now we have to do the average. So now the probability distribution is, of course, h bar squared. Note, again, I'm flipping it. 2i kBt, L times L plus 1. A little Russian dolls there nested. E to the minus h bar squared, L times L plus 1, 2I kb. Okay, so that is the normalized probability distribution. And now I'm going to do this a little differently to get the average energy. So now what's the average energy? The way I'm going to do this is, instead of doing some snarky, like, oh, let's just, you know what I could do is I could just figure out the average L. I can just figure out the average L, but you know what, instead I'm going to put the entire equation, constants and all, into the integral expression. What I did before, by the way, I was just simplifying it a little bit. I could have put, remember I put in n squared, I got the average of n squared, but I could have put in the whole energy expression. I would have gotten the same thing. I just wanted to remind you of the inner mechanics on how these things really work. Now this one, the energy expression is a little bit more complicated. So you know what? I'm gonna do this and integrate the full energy. I'm not gonna do something funny like calculate the average L. That I think I would actually start getting confused at that point. And so what is that like? Now, let's see. Rotational energy is a form of kinetic energy, so it can't be negative. So what I was trying to think of, what were the limits? I kind of blanked out there. Okay, so the lower limit is 0 because you can't have a negative rotational energy. It's a form of kinetic energy. Okay, so there's that. Let's see. Okay, the energy expression is h bar squared, L times L plus 1 over 2I. Okay, so there's this part. Now I've got to then I just rewrite all this stuff, which sucks, but I gotta rewrite all this. Now again, notice it's really just a bunch of constants. L times L plus 1. So this is definitely a little bit more complicated than anything else we've ever done. Minus h bar squared L times L plus 1. Yeah, this one's there's a lot to it in there. 2I kb/t, and I'm integrating with respect to L. Okay. So, yeah, wow. Yeah, this is one of our bad ones, isn't it? Okay, now what do? We find an identity, and again, I had to use my my crazy software to do this. And you know, if you're in your professional life, if you needed this, you would have it. So get this, right? So I swear I typed all this into the, you know, it's the same thing as the website. It's just, you know, like I say, it's just a professional version. And it ends up being 1 over a squared. So you know, I'm just surprised. Look what a giant mess this is, and it turns into something really simple. So here, it looks like I just have a bunch of constants, but then, oh no, wait, sorry. You see what I did? I wrote L times L plus 1, it's supposed to be 2L plus 1. Sorry about that. But remember, that's energy, that's the degeneracy. That's, remember, 2L plus 1, L is 0, there's only one S state, L of 1. There's 3 P states, L of 2. There's 5 D states, right? Sorry about that, little mistake. I caught that when I realized there was a discrepancy between my identity and what I wrote. Okay, so you see how I get what's wrong questions, right? Because this is what happens. All right, so therefore the average energy is so I can get all the constants, h bar squared. There's two h. Notice that there's two h bar squareds. So h bar to the 4. Then I got a 4 I squared. That shows up twice. kBt. So I'm just taking out all the constants, but I noticed that there's a couple of them. So yeah, okay, that's all the constants. And then 1 over a squared, and again, this gets to be a little bit of a headache. A is h bar squared over 2I kBt. All of that squared. Okay, so Now it's just an algebraic nightmare. Writing the same thing again. Okay, then I've got h bar to the 4, now that's still on bottom, then I've got 4i squared kb squared t squared. Okay, those cancel, 4's cancel, i's cancel, kbt squared, so that's kbt. There you go. Now, remember, that's right. This is the average rotational energy for something, for a rigid rotor, for just the diatomic. Now remember that our quantum mechanical expressions, which were for the electron on a hydrogen atom, happen to be identical for a diatomic like O2. So I'm kind of lucky in that regard. If we were not doing O2, it would have been methane. If we were doing methane, the energy expressions, they would have been a little bit more complicated, and I would have had a different result. In fact, I know what my result would be. There would be 3 rotations, so I'd have 3 halves kBt. Okay, but oxygen has 2 rotational motions, 1/2 kBt of energy each, so the total is kBt. Okay, so notice at this point, we have used quantum mechanics to describe the average, the energy, Boltzmann equation to get the average energy of translation and rotation for O2, and we have calculated 3 halves from translation and then another kBt from rotation. 3 halves plus a kBt plus kBt is, of course, 5 halves kBt. So we've done it, right? And then with that, then we can calculate the heat capacity and calculate everything else from there. So there you go. We've bridged the gap between quantum, we looked at a molecule, did all our quantum stuff, got the energies, used Boltzmann equation to get from the microscopic to the macroscopic, and sure enough, it conforms to what you learned earlier in the course when we were, we went easy on you first, right? So it all worked out quite well. Okay, last bit. You know that this thing vibrates, but it technically doesn't count. Now, while the end result will not contribute, we're done in this regard, I am going to do vibration. I'm going to do the vibrational mode of oxygen. And it's going to be kind of a weird looking equation, but I'm going to show you why that equation means that vibration does not count to internal energy. Okay, give me one moment to wipe out the board, and we're going to do that last bit. Okay, last bit, vibration. Same game. What is the quantum mechanical energy? Plug that into the Boltzmann equation, calculate the average energy. Now again, as I mentioned, there's going to be some weirdness to that answer, and there should be because it doesn't contribute to the internal energy. So why not? Well, that's what we're going to answer. Okay, what do we know about the quantum mechanics of vibration? We knew that the energy, which is where we're starting, right, is the quantum number, and there's this 0 point energy. This 1/2 gives us, there's always some 0 point energy. The same thing as a particle in a box, right? Why the n quantum number for a particle in a box, why it starts at 1, there's always some kinetic energy. That 1/2 is the same thing for vibration. There's always some kinetic energy. The ground state is always moving. Okay, now there's a little oddness to this, in which case, let me explain. I am going to drop that. I'm going to drop that half. Now the reason is because it won't affect the result. So let me try to explain it this way. All this stuff I could do with this expression. Let me tell you, it gets really complicated. This half, you know how this thing can mushroom and just blow up. With just a little change in the starting point, this thing just blows up. Well, we can deal with it, get the answer, and guess what? It's no different if the half wasn't there. So it turns out if I just go ahead and remove it, all of this gets way easier. So I'm going to do that. So that's just a nuts and bolts answer that may not have physical meaning, but it needs to have physical meaning. And there is one, and here's what it is. Remember that just like the vibration doesn't count, why is that? What am I ultimately proving here? As I mentioned, vibrational energy to excite a vibrational quanta requires a lot of thermal energy, way more than kT at room temperature has. So kT at room temperature is X amount of energy, like 206 wave numbers, something like that. But like the O2 vibration is like 1700 wave numbers. So kT at room temperature doesn't have enough energy to excite a vibration. So therefore, it's just dead. It doesn't, you can't put energy in. If you can't put energy in, you can't take energy out. So why would it contribute to any of your thermochemistry? The answer is it doesn't. Okay, now for that same reason, that half doesn't matter. It doesn't represent a thing for me to put energy into, and therefore it's not a thing I can take energy out of. Therefore, it just doesn't need to be there. It doesn't affect my ability to store or take back energy. Okay, so that's the physical reason. All right, anyway, All right, now that I have this, now what? Okay, so the probability distribution is going to be E to the minus energy over, this starts out looking a little bit easier, doesn't it? Over the sum. Now we're going to be summing over quantum numbers. E to the minus, same thing. What was that, H bar? I keep forgetting the H bar. Okay. And the lower quantum number happens to be 0, the upper is infinity, which is nice. It's a little bit more complicated if the lower limit isn't 0. Okay. Now this should be drilled into your head. Trust me, this is a review session. What do you do next? You solve the normalizer. Okay. Now it turns out that this is not one that can be turned into an integral. Now there's two reasons for that. One is that there's no justification for it. Think back to rotation 5 minutes ago, and I said that the rotational energy levels are fine. They're finely spaced compared to kT. Vibration is not, so I can't make that approximation. I can't say that it's continuous. I could for vibration, but I really can't with, I could with rotation, but I can't do that with vibration. Okay, number two. I don't need to make that approximation because it turns out that, as usual, what's the identity? Well, there's an identity for this. So if there's an identity, then I'm just going to use it, right? Why wouldn't I? If there's no approximation, I'm going to get a better answer. And you've seen this one before. It was similar to our Planck distribution when we had to normalize that. Okay, so with that, A, of course, is HW over KBT. So, blah, 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 what do we get? Oh, wait, no, that's A to the N. So, here, I got to, look at that, I almost screwed up. So, N is our quantum number, and therefore, A isn't HW over KBT, it's E to the minus, right? There's no minus sign here, so that minus. Okay, so this ends up being a little bit more complicated. I almost forgot that. Okay, so what does this end up being equal to? Same stuff on top. And I don't know why my little, what is that? That's a new. It's a new. Anyway, what's this on bottom? Okay, 1 minus A, 1 minus E to the minus. Okay, so there we go. I hope that's right. Yeah, I think that's right. Okay, so, now we have our normalized Boltzmann distribution. And now we need to calculate the average energy. And to do that, notice that, like before, so the question is, what is this? And it can be turned into what's the average nu times h bar w. H bar omega, the frequency, right? Angular frequency. Okay, but notice that I can just, or I could just throw the h omega in there to begin with. So let's see, how do I do that? So the average energy is going to be sum. It's not an integral. Remember that I don't have a justification. If I couldn't do this with the normalization, I'm not going to be able to do it anywhere else. You ever notice that never happened? Planck distribution, everything was a sum. We had another example. I think I made up some COVID patient problems. Everything's a sum. So here, when we do the energy, everything is still a sum. Okay, and of course, it's still over quantum numbers. And so I've got h omega. There's the thing we want the average of. Wait. Look what I did. Sorry, I keep messing up. It's the -1, right? Right, 1 over. The normalizer is this over 1 minus a. So, sorry about that. So this ends up being, oh, my bad. I'm just really off today, aren't I? Okay. Okay, so there's the real result. Sorry about that. So I lost it. Okay, so then we just plug this stuff in. And notice that this part is a constant. So I know that it's looking like it's complicating, that this looks like it complicates things. It doesn't, it's just a constant. And then we've got same thing. Okay. And guess what? Identity, what's an identity? The identity is, I'm looking for, where's it in my notes? I've gone blind. I think I know this one. Yeah. I was about to say, I think I almost know this one just by heart at this point. A over 1 minus a squared. Yeah, you've seen this a couple of times. Okay, so therefore the average energy is equal to, oh geez, I need some room here. Yeah, this is a bad one, isn't it? Okay, I need a lot of room. Okay, so 1 minus, sorry. Okay, normalizer. Again, I told you that that's actually easy. It just doesn't go anywhere. Let's see, the thing on top, A on top, and then 1 minus all that jazz on the bottom. Yeah, this was pretty bad, wasn't it? And squared. Okay. So that's the answer. But now let's see here. We can simplify it because that cancels out that. So it ends up being not terribly bad looking. Yeah, that's it. Now what you can do is you can actually multiply each side times e to the plus hw over kBt. So notice what that does. That makes the top part, it dies out. And I've got e to the plus hw over kBt minus 1. Okay, so that's actually, is that right? Yeah, so that's the right answer. So actually, yeah, that's really not too bad at all. Okay, so that's the average energy. So now that you've done that, of course, I would never have anything this complicated on the final. Besides, I mean, how did you write all this out? Right, this is kind of bad, right? So we're done. This is just an example problem. Last bit, why does vibration not contribute to internal energy? Well, this by itself is like, well, what the heck is that? What you can do is you can plug in, I have a graph here. Let's say that is like 1700 wave numbers, which is a typical number, what you can do is calculate the average quantum number, which starts at 0 and 1 is the first excited state, as a function of temperature. So I have to have some parameterization for, I have to like plug in something that describes the molecule, and this describes a lot of things. That's about right for a bond energy. Okay, so what I can now plot is the quantum number versus temperature. And of course it starts at 0, goes to 1, and it goes to 2, on and on and on. But that's the ground state and that's the first excited state. Okay, so now let me point out that, again, for this degree of freedom to contribute, I have to be able to put thermal energy in and then take it out later. That is the meaning of thermodynamics. Now, to do that, I have to go from ground state to the first excited state at the bare minimum. Now, we've talked about doing that with light, but I'm not doing this with light, I'm doing it with heat. So now I'm asking what temperature allows me to go from the average ground state of a quantum number of 0, what temperature can I, on average, have excited all the molecules to their first equals 1 excited state. And anyway, this function, let me we'll graph it, minus the h nu, but it looks something like this. Kind of starts out flat, and it just kind of rises linearly. It's a function of temperature. What temperatures are we talking about? I'm doing this in Kelvin. That's around 500. Okay, that's around 200 degrees Celsius, right? So boiling water times 2. Well, I'm not running into that in my daily life. And when do we get to about an excited state of 1? Well, that's around 2,500 K, right? So that's like a blast furnace or a rocket engine. Okay, so, and I'm not joking around here. If we work for NASA and we're designing rocket engines, then you probably would have to take into account vibrational thermodynamics. It would contribute to your internal energy. It would affect how the rocket operates, how much energy comes out of it. If you're working on rockets or blast furnaces for like melting steel. Now, cool, maybe some of you will end up doing that, and I hope you remember this. For the most part, at room temperature, which is right here, it is impossible for thermal energy to excite to excite your kind of rather normalish vibration. So that's why we say it doesn't contribute to its thermodynamics.